Okay, welcome back. So we're talking today about chi-square test. Hi Bella. Gila. How are you? Hi.
I'm good. How are you?
Good, good. Good to see you. All right, let's get started. Let's talk about chi-square test. This is our last chapter. So we're done after chi-square test. We're essentially done with new material. We will be talking next week on Wednesday about choosing the right reporting tests. And this will, however, more of, how should I say it, it's going to be more of a review session. I still highly recommend that you come on, but it's not new material anymore. It's also not tested on, that there will not be a sample quiz, but what you will be tested on is basically to know which statistic you need to choose for each respective research question or analytic question. And this is just very nicely being presented in chapter 18. So we have currently, we're working on homework 3, right? We are basically finished with most of our things. We did all the practice labs. Let me know if there are any questions with anything. We are essentially in, I'm trying to open it. Okay, so this is the 25th module. And we are at this point in time, we are at week 16. We will be moving on to week, I can't actually be that. This is actually week 17. Okay, so we're moving on from week 16, which is this week, to week 17. We're reviewing, and then on the 24th at 1 p.m. This is not our regular time. This is in the afternoon. We will be having final exam. Final exam, 30 questions, 60 minutes. You're going to be fine. You know the sample quizzes. We've spoken about everything quite excessively. I hope I reviewed and repeated things often enough. We can discuss everything next week in the review session. And so there were some questions whether you could do it earlier than 5:24. I wish I could let you take it earlier, and I think it wouldn't be a problem, but I have a date that was basically given to me at which I have to take, have you take the final exam. Yeah, so unfortunately I can't really change that. Those of you in different time zones, hypothetically, I'm okay with you taking it at a different time, but since it's in the afternoon, I'd prefer you come on and you take it with everybody else. Okay, so reserve 1 hour, shouldn't be too bad, shouldn't be too complicated, same system. Basically, the focus will be on the second half of the semester, but don't neglect the first half of the semester. So you still need to know everything that was done in the first half. Okay, yeah, that's pretty much it. So if no questions from your end about syllabus or administrative questions, we can move on and go back to the chi-square, actually where I wanted to start off. Okay. Good. Chi-squared is the only and only parametric test, non-parametric test that we will be discussing in this class. For the reason that it's essentially it's not the leading form of analytic approach. It would not be a go-to, so to say. It would not be your first choice. Only if it's mandated by the nature of the data. So it's either it's skewed data, and it's just absolutely not considered a normal distribution, no matter from what angle you're looking at it. It is just not a normal distribution, or you have a nominal or ordinal dependent variable, which is essentially what you will be seeing today. So it's a special class of hypothesis tests that essentially is used when the assumptions for parametric tests are not met. So what are the assumptions for parametric tests?
That there's a nominal independent variable and a scale or ratio dependent variable?
Yes, goes in that direction, absolutely. But it also needs to be normally distributed.
Yeah, right? Normal distribution.
Normal distribution is the key. So the scale dependent variable is not the only thing. So you can, hypothetically, you still would be asked to use a non-parametric test if it's really extremely skewed. But you're going in the right direction, because as soon as you have a larger sample size, you actually would get away with it, right? So you're half right. So it's really, it depends to some extent also on the distribution, and then it comes down to this really complicated word, which is the homo or heteroscedasticity, where the homoscedasticity means that the variance is essentially the same over the entire range and magnitude of the independent variable. Then you have the assumption of linearity. So when you do, for example, a correlation or regression analysis, you would have to have a linear relationship. If you don't have a linear association, and this is an exponential, or a logarithmic or an exponential variation, you could not use a parametric test, which goes hand in hand with the normal distribution in many cases, not always, but in many cases it goes hand in hand with that. And then fourthly, also independence. All parameters need to be all individual entries need to be independent from each other. So if you have absences versus exam grades, this cannot be the same student having two having two entries from two different semesters. This is not legit. So it needs to be independent pairs. It needs to be independent data points. And if it's not independent data points and you're doing a time series kind of analysis, you need to take into account what is called a random effect. And a random effect, this comes, so those of you who can have further the education into the realm of statistics, you will get in touch at the next level with regression. And regression will lead you to logistic regression and probability modeling, and will lead you to random effects versus fixed effects. Because right now what you're doing with the regression and multivariable regression, you're getting a so-called systematic component, which is essentially fixed effects on your model. And the leftover residual variance that you're not explaining. So remember how we did with R-squared, we had like explained variance over total variance. So essentially the leftover variance and the leftover residual unexplained variance essentially is basically a residual error, and part of this will be improved accounting for random effects. And the random effect is, for example, when you have repeated measures of one individual, what accounts for this one individual repeatedly will account as a random effect. For whatever dynamic you have over time, this will be a random slope, this will be a time-dependent random effect, which basically is characterized by the time, by the dynamics over time. Okay, but this is now something totally different. So basically you use non-parametric tests as a special class of hypothesis tests when the assumptions for parametric tests are not met: normality, homoscedasticity, linearity, and independence of the individual data points. And it distinguishes between pattern and chance when observational pattern, data does not have a scale-dependent variable. And this is where this overview slide is quite helpful. So when you have a scale-independent variable and a scale-dependent variable, you basically would resort to either correlation or regression. If you have a nominal independent variable and a scale dependent variable, you would either use a set test. So this is essentially, this is the scenario where you have on the y-axis, you have blood pressure, and then you have on the x-axis 2 groups, which is male and female. That's a nominal variable. Right? So this is the nominal independent variable on the x-axis and the scale dependent variable on the y-axis. So there's a set test with beautiful normal distribution. There's all kinds of t-tests, follows a normal distribution. You essentially have dependent variable, scale dependent, independent variable, nominal, or in many cases also ordinal. And then you have the ANOVAs, right? Same situation, it's just more groups, t-test with more groups. So when do you use non-parametric tests? When the dependent variable is nominal, when the dependent variable is ordinal, or when the sample size is small and the underlying population is not normal. And this is, Alice, where this comes in, right? It's like, it's sometimes in settings with small sample size, it's not enough to just have a scale dependent variable. You also need to pay attention to the distribution. Once the sample size increases, you basically get away with assuming it's normally distributed, at least to some extent. Good, the limitations of non-parametric tests. Confidence intervals and effect measures are not typically available for nominal or ordinal data. True to some extent, most statistical softwares can still compute it for you. So you still get confidence interval and effect size measures. Non-parametric tests have less statistical power than parametric tests for the reason that they basically account for smaller sample sizes, and obviously they have different degrees of freedom because they're basically looking at nominal variables. As a consequence of that, we know a statistical power prevents us from running into a type 2 error. Where we do have the type 2 error, anybody remembers what the type 2 error was?
Type 2 is a false negative.
Yes, what does that mean?
What do you mean?
What does it mean?
Oh, what does it mean? It means that somebody tells you you don't have it when you actually do have it.
Okay, that's the application then on a diagnostic test. Yes, that's true. And in terms of hypothesis testing, it's kind of the same thing because you assume there's no difference, but there's actually one. So you're missing it because you don't have enough power. On the inverse, what is a type 1 error?
It's a false positive. You think there's a difference when there actually is no difference.
Exactly. So for some reason, usually it's subsetting or it's kind of a stratification kind of story, you are creating a scenario where you actually see a difference, but you shouldn't have seen this difference. So this is a type 1 error. So sampling and subsetting, a common reason that could happen. So type 1 error and type 2 error. So statistical power prevents you from committing type 2 error, and this is more likely with a non-parametric test. So for that very reason, it's not your go-to, because you rather have something which is more appropriate and prevents you from a type 2 error. Good. So chi-squared test now, and these are the only ones we're gonna do. We're not gonna, so there's, you can replace an independent sample t-test with something that is called a Mann-Whitney U-test. You can replace paired sample t-test with a Wilcoxon test. You can replace an ANOVA with a Kruskal-Wallis. We're not gonna do all of these. Know that there are replacements, and I will post a little overview. So there's a very nice overview table that I have at my disposition in a lecture form, and I'm going to post that for you. But it's not the most likely scenario you would run into. What is commonly done is a chi-squared test, and And there are essentially two that you need to know. You need to know a chi-square test for goodness of fit, where you have one nominal variable, and you have a chi-square test for independence, where you have two nominal variables. And we're going to start off with a goodness of fit. We're actually going to do an example. And just like with every other hypothesis test, we have 6 steps. So we identify the populations, we identify the distributions, we make our assumptions, we state the hypothesis, we determine characteristics of the comparison distribution, determine the critical values from a chi-squared table, from a chi-squared table. We calculate our chi-squared value, and then we decide whether to reject or not. So same situation and same approach. And you always have 2 populations, right? So essentially your nominal variable will stratify your populations in 2. For the goodness of fit, you have one nominal variable that creates 2 groups. So you have 2 populations. And you match the frequencies of the participants that are expected according to a null hypothesis where you don't have a difference. So a scenario where you don't have a difference is basically you halve the population and you have half in each group, right? That's 50% in each group. That's half a population. So the comparison distribution is the chi-squared distribution, and we will see in a second what that is. And the nominal variable is an independent observation. So again, it's important. All need to be independent. One entry is only for one participant. These are randomly selected, and you have met a minimum number of expected participants per cell. So there's like a million different opinions. What's the minimum number of expected participants per cell is? Rule of thumb, not less than 5. But there are different varying opinions. Good. What are the characteristics and what degrees of freedom do you have? So the degrees of freedom are determined by the rows. So you have, and the K here stands for the number of rows. You have 2 rows and 2 columns. You essentially have 2 minus 1, 2 minus 1. So degree of freedom for 2 by 2 table is 1, because you have the degrees of freedom for the chi-squared is here. df row, which is 2 rows, minus 1 is 1. 2 columns, 2 minus 1 is 1. You basically get 1 multiplied by 1 is 1. So degrees of freedom of chi-squared is 1. And you will look this up in a chi-squared table. So, and this is where I want to move away. And I have posted this on Canvas, the chi-squared table. No, actually did not. Let me do that right now. So the chi-squared table is essentially a unimodal right-skewed distribution, which essentially, so you see it now in your module. I've posted it now in the module, and now we're going to look at it right here. So this is the chi-squared. So it's a unimodal right-skewed distribution, which essentially is showing you different chi-squared values and will allow you to essentially make your determination based on that chi-squared. So as soon as your chi-squared value exceeds your critical value, which you're going to find here, for one that's actually not on here, exceeds your critical value, which is here for our example, it's going to be 3.841 for a p-value of 5. We essentially reject in a one-tailed hypothesis test on the chi-squared distribution our hypothesis, our null hypothesis. So this is how that looks like. The degrees of freedom are here determining the rows. The columns basically determine the critical threshold and the probability of this being just random chance, as extreme due to random chance. So if we're going back now to our example, we are basically now working on an example which involves now, for the goodness of fit, a degree of freedom of 1 and a critical chi-squared of 3.841. And as soon as the chi-squared is exceeding 3.841, we know that the p-value needs to be smaller than 5%. So now the example is the following. Okay, let's not show the next slide because now I want to show you the example. So following example. So there's actually, believe it or not, there's research that basically hypothesized that when a kid is born in the first half of the year, it's more likely to become a really good soccer player or football, as we call it in Europe. So essentially, when you have 52 elite youth players that were born in January, February, or March, and only 4 players were born in October, November, December. One of the possible scenarios could be that if you say, okay, you're born in the first half of the year, you essentially are more likely to be a good soccer player. So if you map this now out as a table, okay, so we say first 3 months of the year, and then last 3 months. So we have here observed values, right? So we have observed 56 players. 56 players are distributing with 52 in the first 3 months. This is observed. With 52 in the first 3 months. And we have 4 that were born in October, November, December. So 4 were born in the last 3 months. So this were observed. So we want to test now whether this is actually significant as an observation and significantly different from what we would expect under the null hypothesis that there's no difference of your football abilities when you're born in either period of the year. So we're seeing here skew towards being a good soccer player once you're born in the first half of the year. When thinking about it logically now, how would it look like when you had to think about what's being expected? So if this is balanced and not skewed in any way, and you don't have a greater likelihood to become a good soccer player because you were born in the first month, this would need to be half of the total, right? So if you have 52 and 4, this is 56. 56 divided by 2 is 28. So this would be what you would expect. So now the chi-squared test is essentially calculated by calculating and standardizing the difference between observed and expected. What does that mean? So if I have, so let's abbreviate observed as O and expected with E. If I calculate the difference between O and E, I have here observed minus expected, right? That's 24. If I do the same thing with the last 3 months, I have minus 24. And now it's getting, so you know what we always do in statistics, at least at this level, whenever there's a direction involved and we just want to quantify the deviations in a standardized way, you square that thing. And you basically get a squared deviation. So it's once again, it's the same kind of approach as we have done right from the start, right? So it's basically, it's not a sum of squares, but it goes in that direction to some extent, right? So we're having a difference, we're squaring the difference, we are appreciating the differences in a standardized fashion to what exactly we're looking at. And this is what we're doing now as observed squared. Now we're putting a lot of, no, actually we don't need it. Standardized to the expected. By that, you get the difference standardized to what you had expected in that group. So you essentially calculate now 576 squared divided by your expected count. And this is 20.571. And we're doing the same for the second row for the second half. So it is because the difference was the same, it's obviously the same value. And now when you want to quantify the chi-squared, the only thing you have to do is you sum this up and you have your chi-squared for the goodness of fit. So this is the chi-squared for goodness of fit. And this is super easy, right? It's a little bit more involved for the test for independence, but this is the principle. So you basically calculate a difference between observed mass as expected. You square this thing, you add it up, you standardize it to your expected, and then you sum it up. And that gets you that chi-squared. And this is the chi-squared, which you then use to compare it to your critical threshold. So now with 41, you are significantly rejecting a null hypothesis. So again, believe it or not, there's actually there's actual research around this. So there are actually there are hypotheses out there that it could be because what was it, like the UV light you get in your early years of life, and so there are kind of theories whether that actually could be. So I personally would not be too convinced, but again, it's just me. Okay, so this is the goodness of fit. And this is really the simplest form of a chi-squared test. So now let's move on. Okay, so this is this calculation, and this comes to this equation. No, no. Okay, so we are working with this equation. That's the equation we're using to quantify the chi-squared. So again, this is chi-squared equals the sum of observed minus expected squared, standardized to the expected, standardized, right? And we are now moving on to the next example. Okay, so we did this, we came to that. This is simple, right? So now we're testing for independence. So the goodness of fit and the test for independence follows the same same strategy. The only thing that's different now is like now we have 2 or more nominal variables. So testing a chi-squared, you can actually do this at like a large number of cells. If your processing power is good enough, you can do all of that. Essentially, you would not, yeah. So there are different methods out there for different categorization, larger scale. But essentially, also you got to keep in mind that essentially you get one hypothesis test, right? If you do a chi-squared test, you get one value. You get one shot at this because you have expected for each cell. And then you basically say, okay, so that's what I'm seeing right in front of me, what I observed in my cells on my table, on my contingency table, is different from what I would have expected. And then you're basically done with the interpretation. The only thing you can do then is post hoc testing, where you do multiple testing again. Same scenarios with ANOVA. You have, you basically get one result for all. You reject, means like one is different. And once one is different, then you basically have to compare each of them to basically get a difference and understand the differences that you're observing. And you can do this with binomial tests, for example, but we're not going to talk about this. We're sticking with the chi-squared alone. So, okay, comparison distribution, chi-squared distribution, hypothesis test is a chi-squared test for independence because we have two nominal variables. Can you state this hypothesis? So the hypothesis here is really the null hypothesis that there's no difference between observed cells and expected cell entries. And this is essentially, it says that there's not one cell significantly different from your expected cells, cell entry, cell counts. So now the example is, and you have that in your book. So, you know, I don't know what kind of coffee you prefer. Sometimes you go to Starbucks and you order your coffee and they write your name on the cup, right? So once that actually happens, you become emotionally attached to your cup. And even if that name is even spelled correctly, so my first name is Jochen. You can only imagine how my name gets slaughtered. So it's really it's not a joke. So if it's spelled correctly, you're so flattered that you essentially are more likely to recycle your cup. If it's incorrectly spelled, you're less likely to observe it, to recycle it, and then you're more likely to trash it. If there's no name on it, you're also more likely to trash it. So I find it kind of an amusing example, but it's interesting. On psychological level, it's interesting. And so now these are our observed counts, right? So we do have a little bit of a gradient. So correctly spelled name actually is not that obvious of a difference, but it leans overall more towards being recycled. As for the trash, you basically, so the correctly spelled name, least likely to be trashed, whereas incorrectly spelled or no name, clearly a gradient of being more likely to be trashed. Good. So what are we doing? We're looking at our populations. We're determining the characteristics of the comparison distribution. So we have df row equals k row minus 1. So k row is the number of rows. We have 3 rows. Minus 1 is 2. df column, we have 2 columns. Minus 1 is 1. So 2 multiplied by 1 is 2, which means our degrees of freedom, our chi-square's degree of freedom are 2 multiplied by 1. So it's 2. So the critical value or cutoff for the chi-squared is then on the p level of 5%, 2 degrees of freedom. We are looking at, no, we're not looking. Okay, the expected frequency is the most important part for the calculation. Yes, so we know that the threshold now is 5.991. And I'm going to show you in a second why. So must I find this again? Yeah. Okay, so we have degrees of freedom for chi-squared of 2, right? So it's 2 columns, 2 minus 1 is 1. There's 3 rows, 3 minus 2, 3 minus 1 is 2. 2 multiplied by 1 is 2. And our p-value threshold of 5% gets us to degrees of freedom of 5.99. Good. So this is this. So now we're moving on, and we're coming now. No, come on. Okay. So I have reproduced here this little table, and here's the example for you to read up on. So we have 53 given on paper cups. So they basically created 2 groups, right? So it's like, is it randomized? No, I don't think it's randomized. You would need to have it randomized, right? Because what could be a confounder? Anybody who has an idea, what could be a confounder here?
The location of the coffee shop. So if it's in a very hipster neighborhood, they might recycle it more. Whereas if it's in a different place, it might be.
Mm-hmm. That's a very good thought. Very good thought. But would that be a confounder or would that be a bias? I would be
It
selection
might
bias,
be,
right?
it might actually be a confounder because perhaps in neighborhoods where there's like richer folks, there's kind of an interest in providing good quality so that they would tip you.
Okay. Okay. Okay, I can see that. I can see that. All right, good example. What could be another confounder? If you have two groups, right? So you basically, no, actually you have three groups. So you have correctly, incorrectly, and no name. What if you have a disbalance of those with a really complicated name versus those that have a really simple name? So that would be definitely a confounder, and you would need to have this balance between the groups to essentially make sure that this is not confounding your insight. That would be a very classical example. The neighborhood is an interesting one. Yeah, there are definitely ramifications to that. I could see a couple of interactions there. Yeah. So yeah, good thinking. Very good. So now we have these 6 different cells, right? So now we have 53 in each of them. So we have here 25 and 13 and 14 is 53. Didn't they say 53? Let's put it in. Either I copied that wrong or what? Hold on. Only 13 was a cup. 13 cups, no names. 14, 13, 14, 25. Okay, so we have, okay, 25, 13, and 14. 25 is 38. This is 52. Okay, so one has not gotten his coffee. Okay, not sure I'm understanding that. That's an interesting example. Okay.
I realize now that because it's an experimental, I thought it was just observations, that location wouldn't be really relevant. They all do it probably in the same place with the same coffee shop.
That depends, yes. And so if you choose different locations, it definitely changes. You got a point there, like location. I'm not discarding location per se, but you would need to kind of have different locations. Otherwise, you're implying that location has overall effect on the perception of your name. So that's the implication of you. And then this is where I meant like this becomes an interaction at this point. It's getting a little more complicated. It's not a classical confounder situation anymore. It's more of a selection bias. Okay, so I'm having here an arithmetic problem, but thanks for contributing your thoughts, Alice. That's great. So we have here sum. Okay, this is for the 53. Okay. So I tend to not trust myself, so I thought I have a transfer error, but it's not a transfer error. So we have 53 here. Okay, so my past me did the right thing. Okay, so we have 53 in each group. We have 53 that have the name spelled correctly, 53 that have them incorrectly spelled, and 53 have no name on their cup. Good. What are we going to do next? We need to determine now what is expected and how we're going to expect this. If we were to determine, this is now we'll bring this back in. If we were to determine what is expected for the first group, with 53, 53, 53, that's 159. If we were to determine for our cells, so this is outcome, right? So the outcome is recycling or trash. So we have 52 and 107. So if this were balanced between our exposure groups, we would need to divide our marginal total of recycling by the number of groups. And then we get a balanced outcome, balanced count. So if we do this now, so let's bring this. Okay, so we have here recycling. Okay. Then we have here trash. Then we have correctly and incorrectly spelled. Then we have this. Okay. So now we have this. Okay. Okay. Okay, so we're bringing now our white format, and I may have spoken about it already with the ANOVA because we have the kind of same situation here. So these are all observed, right? We've observed this, now we want the expected. And the expected we're basically calculating now is 25 plus 13 plus 14 divided by the number of groups, right? So if we do this divided by 3, we are getting our 17.33, and this is our aliquot in each of the group for what we would have seen if that were balanced. So this is our expected. So if we want to do the same now for the, sorry, if we want to do the same for the other group, we need to do K8 K8 divided by 3 gives us 35.67. So this being said, we have now here our expected. Is that clear why that is the case? So we essentially do nothing else but balancing amongst our group. We have 52 randomly sampled individuals have taken their cup and recycled it. 107 have trashed it. If this were balanced between our 3 groups, we essentially would have seen this number. So what are we doing now? We're doing the same as with the goodness of fit. We're calculating a difference between observed and expected. And this difference essentially is now in the next step squared. So we do O minus E squared is now observed minus expected. And don't forget the brackets in case you ever do that by hand. Now we can just, and this is the reason why I brought in a long format, because it's just much easier to do that in that fashion. So now you have this squared. So it's lacking a direction. So it's a one-sided test, right? Because you're going in one direction, you're quantifying this difference now, and you're standardizing it now. You're standardizing it now in the next step by the expected. It is not this divided by this 3.4. So, and now in the last step, you just need to sum this. And the sum is your chi-squared. So this is your chi-squared, 7.61. So, $1 million question, are we rejecting this or not? We go back to our slides. We go back to our slides. Okay, same thing. In calculation, we can calculate. Can copy this in here. Just for the sake of having it. Okay. So this chi-squared, we're comparing this now against our null hypothesis. We remember that 5.99 was our critical value. Our 7.062 are exceeding 5.99, and we're basically rejecting the null hypothesis. Okay, it's pretty simple, right? But as a concept, as soon as you have the concept, it's pretty clear what you're doing. So now it's getting a little bit more complicated. So now we want to standardize this. So now we want to standardize this because by that we're getting a residual from our expected, which is kind of nice because that kind of leads you towards understanding which group is actually more deviating from what you expected. And this you would do with the quantification of an adjusted residual. And this is essentially the difference between the observed frequency and the expected frequency for one particular cell in a chi-squared research design divided by the standard error. And yes, you have a standard error because you have all your counts are basically giving you a distribution of the mean differences, right? So you are back to having a standard error. So now this calculation we're not doing by hand. For this very reason, I have read this whole thing into R, and I have the code posted for you. I just want to quickly show you that. So this is just that you understand what this actually is. And Nolan and Heinzen have here in, okay, they have in the Launchpad and also in the book, you will see the adjusted residuals in a software format, which I absolutely only showing for the sake because they used it. So this is SPSS. So you basically see a count, you see an expected count, and this is consistent with our data. And here you have adjusted residuals. And these adjusted residuals obviously require for you to know what is the standard error of the mean, which is basically the differences quantified by the sample size, as you know, right? So the automatic calculation that we're doing is in R. It basically gives you the same results. This is our little table, 25, 30, 14, adding up to 52, 28, 40, 39, adding up to 107, I believe. So now, if we are doing this analysis and we're building a chi-squared, so this is the code for running a chi-squared. It's chi-squared.test. If you are to run this up now, you essentially get your chi-squared result. And yes, here you get chi-squared of 7.601. You get a degree of freedom of 2 with a critical value of 5.99. You get a p-value of 0.02. And yes, you get a p-value. So this is the beauty of having R or having any other statistical software, essentially, because it gives you a p-value. It basically uses the area under the curve, under the distribution curve, to quantify the probability and get you the actual p-value. So,
and this is significant because it's 0.022.
Exactly, it's smaller than 5%. It's the same principle, right? So this is a one-tailed hypothesis. We're basically exceeding the critical threshold where the p-value is 5% will result in a p-value smaller than 5%. So we exceeded this critical threshold and the p-value is actually smaller than what we see. So in essence, what you are looking at, and this is what I cannot emphasize enough, the area under the curve is the integral of this function. So let's preview now. Preview disappeared to me. Okay, let's find it here then. Okay. So when you look at this, so you basically, this just like the normal distribution, and you remember I think it was like session 6, where we had like the normal distribution. The normal distribution follows essentially a nonlinear function that builds out Gauss's bell curve, right? Same story is happening here with the chi-squared distribution. This essentially is one mathematical function, which essentially has what it's called an area under the curve. So you can, integrating this function will allow for you to calculate the area under this curve, which you, in case of further your statistical education, you will do at one point, because this area under the curve allows you to quantify the probability under that curve, right? You remember how we had area under the curve, and we had those probabilities based on the set scores distributed under the normal distribution curve. Same story here. You basically, you have a threshold. You quantify this area under the curve and you compare it with the overall area under the curve. The entire area under the curve is 1. This area under the curve here is exactly 5% of it. So now you move further up and you have 7.601. You are somewhere here, and the rest of this area under the curve is your probability. This is your rest p-value. So that tiny little tail on the top that you're basically quantifying then as the area under the curve, that's your p-value. And this is what R is doing. It basically takes this function and it basically uses the function, integrates the function, calculates the area under the curve, gets the p-value back. That's all it does. You could hypothetically do this by hand. I encourage you to do it because it's good exercise, but it's like R does it for you. Does that make sense? You all with me? Good. So, okay, so we have the chi-squared observed, which is exactly what we've seen, chi-squared expected, exactly what we calculated, chi-squared residuals is now our standardized adjusted residuals. So this is essentially consistent with what Nolan and Heinzen are showing here, and is essentially, yeah. Oh, wait. No, those are actually the not standardized residuals. These are the standardized residuals. So residuals, again, residuals can be standardized or can be not standardized. Here it's actually standardized residuals. So again, why is this relevant in the greater picture at this point in time? It's important for you to know for the sample quiz chi-squared. As you will do it, you will likely use it for the comparison of nominal groups. You will need to know that when there's one difference from your expected count, you get a p-value smaller than 5%, and you know that one of these groups is different. How you do the post hoc testing is then basically what you need to know. And this is like an exact binomial test, which you need to do for the groups that are actually interested for your research question. We will not be doing that, but we have done so when we talk about binomial distributions. But again, this is an introductory class, and I think the chi-square is enough at this point. Good. All right, so we have this now. What are we doing next? So we have calculated now the adjusted standardized residuals. And in the next step, we are now with that, adjusted residuals. And as you know, there's always an effect size to be calculated, and this effect size essentially is dependent on your chi-squared, on your sample size, and on your degrees of freedom, either row or column, whatever is smaller. Because you basically want to have a very conservative estimate of the effect size, right? So whatever is smaller essentially is what you will be using for the multiplication with the sample size in the denominator. So your effect size for our example here is now, let's bring that over. Our effect size for this example here is So this effect size, yeah, and this is Kramer's V, and it's V like Victor. So I know that yeah. So that's my German accent, V and V. Okay, so it's Kramer's V like Victor. So we're doing now, essentially we're using the square root and the chi-squared divided by the sample size multiplied by the degrees of freedom. So we're doing Kramer's V. We're doing a square root of chi-squared divided by n, and this is now the sum of all that were essentially assessed, multiplied by our degrees of freedom of row and column, whatever is smallest. Degree of freedom of row and column is 1, right? Because we're taking the column, that's 2. That's the k column, minus 1 is 1. Multiplied by 1, using the brackets, and this is our V, 0.22. So now 0.22 is just like we always do with effect sizes. We're comparing this against Cohen's conventions. We have degrees of freedom of 1. We have with 0.22, so we have a small effect size, a significant effect size, but it's considerably small. And yeah, and this is how you determine effect size. Fairly simple, right? It's not complicated. So the chi-square generally is like considerably easy. Yeah, it's important to know. I think the concept is somewhat a little bit more challenging than the actual calculation. And I just always want to do the calculations and emphasize the calculations because that's the gateway to understanding the test. Okay, so now when you actually want to present this, and you would present this to, let's say, I don't know, for whatever reason, so you want to show this in your research paper, and you would then need to find ways how to actually show that. And one of them, and you remember that I'm not a big fan of pie charts, right? We talked about that. Pie charts are rather uninformative. So for this very reason, we're going to do bar charts. And this is essentially how you could show these. This is essentially how you would be showing these. So you're comparing each of those groups against each other. And this is also what you then essentially, if you were to choose post-hoc testing, you would actually compare these nominal groups against each other. All right. So these conditional probabilities are considerably easy to be calculated. The only thing you would need to know is each group. So you essentially do nothing else but calculating the probabilities of each of these groups. So you have a certain marginal total, right? So you have correctly spelled name, incorrectly spelled name, and no name. We have observed recycling, observed trash. And this. And now we essentially do the actual entry divided by the marginal total. So this gets you a proportion. So you have here 0.47 this is your proportion within your group. When you do the same thing here, and you divide it by the 53, you get essentially the inverse, right? So overall, you can now calculate, this is a sum, will add up to 1, right? And adding this up to 1 feeds you to the marginal total. So this is now, you can continue all the way down. And this is basically what you would use to depict as your bar chart. Right? So you would plot this as bar charts, and you can actually quickly do that. Oh, I post the code. I post now code. Let's see now. Because what I want to show you in particular is now what's actually, we have 13 more minutes. Okay, that's actually good time. Okay, so we can do simple graphs and easy graphs. I'll show you a quick graph. I'll show you the more complex one in R, because it's just not additional. Okay, bar graphs. Okay, so that's a bar graph. So essentially what you need to do, you just need to, I think it's stuck. Oh, yeah. Okay, so this is basically how you can easily build these graphs. So you can essentially show for each of these groups the difference, and this would basically be the way how you would do that. So you've seen the only thing you need to do, you're just trying to select the entire matrix. You click on graph, and you literally have Excel figure it out for you. Good. So this is considerably easy. And now we can do something which I think is quite important. I believe I read that some of you are going to go in the medical field, and that's particularly important. So it's for me in epidemiology, it was like something I very frequently did, relative risk. So in the psychology field, I'm not certain how often it's being used, but in medicine and public health, definitely very often. There's marginal total. So if you were to calculate the relative risk of, so this is a proportion, right? This is a proportion of this happening. So if you wanted to calculate the relative risk of somebody trashing his cup when having a correctly spelled name, or an incorrectly spelled name as compared to a correctly spelled name. You can do this by taking the proportion correctly versus correctly versus incorrectly spelled name. So if you were just to compare this, trash correctly versus incorrectly spelled name, you're just interested if somebody gets an incorrect spelling on the cup, how likely will it be that he or she will trash the cup? And you're doing that by basically taking the probability of trashing was an incorrectly spelled name divided by the probability of trashing it with a correctly spelled name. Because what you get by that, you get the so-called risk ratio or relative risk. And you get it relative to the risk in another category. So essentially what that means, the interpretation of this is now that the risk to trash with an incorrect spelling is 1.42 times that of trashing it with a correctly spelled name. Or alternative, because if it's 1, it's the same, right? So then there's no difference in the risk. But if the risk changes and it gets larger, it's important that you understand which one is your reference group. And if it gets larger, you're essentially increasing your risk. So there's a clear risk increase. So we used the reference group here is correctly spelled name. So you usually always take kind of the more conservative estimate. So if you say, okay, name is spelled correctly, I'm least likely to trash it. But now somebody spells my name incorrectly, I'm more likely to trash it. So you basically, this is the angle you're looking at this. And the angle you will be looking at this is dependent on your research question in most cases. So now in this regard, you're quantifying what's the risk increase if my name is incorrectly spelled as compared to having correct spelling. So it's 1.43 times the risk to trash it with the correct spelling. Alternatively, so 1 would be the same. Less than 1 would be a protective factor, which would the implication would be if somebody spells my name
Professor?
We can't hear.
Oh, thank God it wasn't just me.
It's gone.
Oh no, where'd he go?
I really thought it was just me for a minute. I was like, oh my God, I cannot hear him anymore.
Yeah, I was muting and unmuting and
hello, can you hear me?
Yes.
What happened now? Did
you were ejected. You left.
I did?
Yeah.
Interesting. I don't know what happened really. Yeah, sorry, no idea what happened. Okay, good. 1.43 times the risk. All right, can you see my screen? Yes. Okay, you can see my screen, you can hear me, good. Okay, any questions to relative risk? So as you can imagine, these are things that are important when it comes to diagnostics. So you have, I don't know, you have, okay, we didn't speak about conditional probabilities, but now when thinking about COVID as a diagnosis, when they ask you, when you enter a restaurant and they ask you like, did you have fever in the last 2 days? Did you have contact with anybody? So this is basically, you are basically moving from one group in another group if you say yes to one of these. So you are quantifying the risk increase with a condition that is basically indicative of you having contracted the disease. So this is where risk ratios and relative risk is quantified quite often. I hope the recording didn't stop. We're almost at the end of it. Is what?
It's on.
Is that okay? All right, good. Weird. I don't know what kicked me out. Okay, so this is the relative risk, the relative likelihood. We talked about that. Is a ratio of two conditional proportions. One group is 3 times as likely to show some outcome. So it comes to the same thing. It's 1.4 times likelihood ratio cup once your name is spelled incorrectly. Yeah, and this is all that I had for today. Any questions? No? Okay, then we can actually conclude for today and wish you a nice evening. See you next week on, how was it? Wednesday, I believe, right? We're gonna go through.
Thank you.
You're welcome. And we're gonna do a fast walkthrough through the entire semester. All right.
Professor,
Yes,
wait, can I please talk to you for a minute?
sure.
First of all,
Yes,
wait,
no.
do we have class on Wednesday?